Hey everyone, how's it going? So today we are going to be talking about bond hybridization. This is going to be the second part of that video of the Vesper video I had last time. So let's just kind of just jump straight on into it. We're only going to be talking about hybridization today. Hybridization is whenever you kind of mix two different types of orbitals together, and that hybrid orbital kind of looks like both of them a little bit. So what are the types of orbitals that we know about? Well, we know there's an s orbital, and we know there are three p orbitals, there are d orbitals and f orbitals. But so the only thing that's going to be on this exam, you can see right here, that d orbitals and above will not be on the exam. So what you're going to be really worried about are the s orbital and the 3p orbitals. Okay, so those are the orbitals that we're going to be mixing together, that we're going to be hybridizing. One thing that you're going to need to know about this is the bond angles for that. We've already talked about bond angles in the Vesper video. How does hybridized things change that? What's the difference between a pi bond and a sigma bond? So a little bit of review on orbitals first. Orbitals, they of course are where the electrons live. That's where they exist. You can think of them on this energy diagram, but if you want to think about them in geometry wise, you need to think about them like this. Remember, s orbitals are the sphere. P orbitals kind of look like these little dumbbells, and there are three p orbitals here. There's one going on the x-axis, y-axis, and z-axis. And whenever we hybridize these guys together, we're going to be hybridizing 2, 3, or all 4 of these guys together. Whenever we do that, if we're hybridizing all 4, we have S, P, P, P. So 1s and 3 p's. And the term we use for a hybridized orbital that has all 4 of them like that is SP3 orbital. That's kind of the way I usually go about and look at it. I think, how many electron groups do I have? And then count on my fingers SPP, that's SP2. If there's 4 electron groups, SPPP, SP3. If there's 2 electron groups, SP1. That's kind of how I go through and determine what hybridization state these electrons are in. So let's talk about what is the difference between a sigma bond and a pi bond. So first, let me just go through and talk about a sigma bond. A sigma bond is orbitals that just overlap, if you see any type of overlap. So if you have 2 s orbitals, and if these guys get close together and they start to overlap, that's a sigma bond. If you have an s orbital and a p orbital, this is just a normal p orbital, an unhybridized p orbital. If these guys overlap, bam, that's a sigma bond. So with p orbitals, if these p orbitals are in line with each other, if they are in the same plane and they overlap, that means you're going to get a sigma bond. The important thing here isn't necessarily that they're s orbitals or p orbitals. What matters is the overlap. If you see an overlap, that leads to a sigma bond. When we talk about pi bonds later on, I'm going to point out there is no overlap. So let's actually take a look at one of these hybridized orbitals. So in this case, we're looking at SP3 hybridization. So we have one s and then 1, 2, 3 p orbitals, and these guys hybridize. They're gonna, instead of these 3 looking like p orbitals and this guy looking like an s, they're all gonna get blended together and kind of merge into one type of orbital. So we still have 1, 2, 3, 4 orbitals. That means we still are going to have 1, 2, 3, 4 orbitals, but they all look the same. The only difference is that they just are facing different ways. This one's facing straight up. This one's facing down and a little bit away from us. This one's facing down and a little and towards us. This one's facing down and away from us to the right hand side. And if you remember from Vesper, these electrons all want to be as far apart from each other as possible. And so this is kind of the orientation that they're going to have. Now, where have we seen this tetrahedral arrangement before? No, yeah, it's part of VSEPR. Anything that has 4 bonds associated or 4 electron groups is going to have SP3 hybridized orbitals, and that's what gives the electrons that the geometry and all of the bond angles and all of that. So SP3 hybridization is going to have a bond angle of 109.5 roughly. Why exactly do we even have SP3 hybridized? Why do we even have SP3 hybridization going on? All has to do about less energy. Remember, in chemistry, everything just wants to be stable. Everything wants to be at that ground level. Everything just wants to have the lowest potential energy. Everything wants to just be chill out. Let's take a look at an energy diagram, and you can see what I'm talking about. So this is the energy diagram of orbitals in a free carbon atom. You see 2s, and here's the energy level of the 2p orbitals. But when you hybridize them together, they're all the same type. It's still 4 different orbitals. So 1, 2, 3, 4 orbitals, 1, 2, 3, 4 orbitals. But they are all identical. They're at the same energy. Now you might be thinking to yourself, well, hang on. This 2s had to increase its potential energy to become like that. That's no bueno. That's not good. It doesn't like that. But these p orbitals all lowered their energy. When you're looking at what the total energy change is, it actually is negative. It is more stable, less potential energy than if you have it separate 2s and 2p. So if you have the electrons to do it, it looks like hybridization is the way to go if you're looking for finding the most stable configuration. So that is why we actually have these hybridization states going on. So it's not just SP3. You can have SP2. You can even have SP1. If you have just one S and one P, that will be an SP1 or SP hybridized hybridization state. So how do you know what it actually looks like, and what does it look like when you have this mix of hybridized and unhybridized orbitals? Well, let's start with a Lewis structure. So this is the Lewis structure for ethene, and we see that there are 1, 2, 3 electron groups in this around this carbon, which means it's going to have sp2. SPP, 3 electron groups, so sp2. Now, that doesn't mean that that other p orbital disappeared. It just means that it's still an unhybridized p orbital. These guys, the sp and the first 2 p's, hybridized together. Now they all look like sp2s, and we have 1 p orbital left over. So it kind of looks like this, where you have 1, 2, 3 sp2 orbitals, and then 1 p orbital going above and below it. So if you go through and see, it's going to have the same type of thing going on with both carbon atoms. So we get something like this, where we have the carbon and carbon. Here are the sp2s. We have the hydrogen, which is going to have a s orbital. And these guys are all going to be bonded together. And if you see here, we see that overlap. There's overlap, 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 and overlap. All of these guys are sigma bonds. Now, one thing that this middle figure does not show is the p orbitals. So here we see that we have the p orbitals, and there is a bond going on, but there is no real overlap. There's no overlap in these p orbitals, but they're still bonded together. Electrons are still going back and forth across these little bridges. This is a completely different type of bond. There is no overlap, and since there isn't an overlap, this is a sigma bond down here, and then these guys is a pi bond. So you have one p orbital here and one p orbital here, and they're connected with two connection points, this two little bridges, but it's not two bonds. This entire thing is one bond. One bond because it's connecting two orbitals together. So this is one pi bond. So if we look at something like nitrogen, and if we draw the Lewis structure of nitrogen gas, we see that it has a triple bond and a lone pair. So this would be two electron groups, which would mean that would be 2sp, so an sp orbital. There are still two orbitals there, so we have one orbital, that's an sp, one orbital, that's an sp, and then we have a p orbital, that's a dumbbell, going here, and we have another p orbital, that's a dumbbell, going here. So that's still all of our orbitals, sp, p, p. 1s, 3 p's. The first s and p hybridized to make an sp here and sp here, and then the last two p's are going this way and up and down. Now, if we looked at something like this Lewis structure, we know that the lone pairs have to be in an orbital, and we know that we have one real sigma bond between the two nitrogens. So if we look at just the hybridized orbitals, we see that we have a lone pair in one of the orbitals. We have these orbitals overlapping, forming a sigma bond, and then another lone pair on the other side. So we've taken care of these lone pairs, and the sigma bond in the middle. But with the Lewis structure, we still see that we have two other bonds. Those are going to be your pi bonds. I'm going to use two different colors for this. So the first one is this p orbital and this p orbital are going to be binding together. And remember that if two orbitals are connecting, it's just going to be one bond. So this one bond in green is going to be one of our pi bonds. So that means that this bond is going to be actually a pi bond. The second pi bond, I'm going to draw this in orange, is going to be this p orbital going up and down, this p orbital going up and down, and there's the pi bond. So this is going to be our second pi bond. So this is actually that pi bond. When you're looking at these two nitrogens, I know it looks like there's 1, 2, 3, 4, 5 different bonds going on, but remember that these two are both the same pi bond because it's just connecting these two orbitals together, and these two orbitals are connected with this middle pi bond. Okay, so that's going to be it for today. Little bit of hybridization. This should finish up Unit 2. We'll move on to intermolecular forces next. I will see you guys later.